x1 through x2g, and the product, I've got a single relator, the product of these commutators. And I'm using some shorthand here rather than actually writing out the actual presentations, but yeah. So I can list all the at least one presentation for all surface groups. This lemma tells me I can in fact list all presentations for surface groups. Okay? Which is good, because it means if I'm trying to determine, is this presentation a presentation of a surface group? If it is, it will eventually show up on the list. Right? And then I've got it. Make sense? So sort of, do I want to say sketch or do I want to say proof? I guess I would say.
P only contains presentations of groups in C.
Oh, good point. Presentations, yes. Otherwise, this doesn't work. Yeah. Of groups, yeah. Of groups. In C. Yeah. Only groups in C. And I've got every group in C at least once. That's important, yeah. If I had a group that was not in C, then whatever. I can certainly list all presentations, and that doesn't tell me anything about the recursive enumerability of the class that I'm interested in. So what I want to say here is, so this basically boils down to using TC transformations. So there's an old theorem of TC from 1908, I think, that says that if, say we've got P1 equal to, say XS, and P2 equal to Y, sorry, X, we'll do X bar like I've been writing, and Y with relators S are presentations for the same group. So there is a sequence of transformations, a finite sequence of transformations. So we're starting with this x0. So this is just x with r, and that's my x0, r0. And then I transform it in some way that I'll tell you in a second. R1, and so on, up through xn, Rn, which is supposed to be my target presentation, P2. And of course you can call them this, I'm sure. Some transformations. Okay, and what are TC transformations? They're the simplest kind of things you can think of that get you a group which gives you the same presentation. So one thing I could do is I can add a relation that's a consequence of the old relations, right? So we've got R, even the singleton R, where R is in the normal closure of R sitting inside the free group on X. So that's the first type, and then the second type. I can add a new generator and just set it equal to some word. It doesn't matter which one. I just pick some word in the free group on X. So, and that's my new relation. So I've got X inverse W for W in the free group on X. Okay, so I know that if these things are isomorphic, there's this finite list of transformations that gets me from one to the other. But I have infinitely many choices of transformations I can make at any given point. So that seems bad, but it's okay. It's a recursive. The set of available TC transformations is itself recursively enumerable. Right? And so I have this recursively enumerable number of choices to make at the first step, and the next step, and the next step. So you can actually list, you can put that all together in one algorithm, in one sort of machine, and list every possible move. Right? And then do that in parallel for all your recursively, for all the presentations in P. So you can check this. So this is a fact or an exercise or something. So that the set of available Tizzi transformations from say x0, r0 is itself recursively enumerable. Okay, and then consequence of this is that you can list all presentations obtainable from those in P by Tizzi transformations. I'm going to just draw a picture. I don't know if this will make things clear. Well, you can do this, but you should go away and think about it if it's not clear. So you got your presentations in P, right? So, and I have some procedure to list them, but I don't just want to list them all. I also want to list all the presentations that I can obtain from them. So I start out by just listing one, and that's my first step. And now I list the second one, and now I do the first available Tizzi transformation on the first one. Okay, and that's my second step. And so then the third step is, well, I need to list the third element of P, and now the first Tizzi transformation I haven't done yet on each of these guys. So this is going to be like this, and so on, right? So you just keep going, and eventually you get this forest, this countable forest of countably infinite valence trees, and you would get every vertex in each of those, and that gets you all the presentations that you can get from this recursively enumerable set of presentations. Okay. So right. So
Just
yeah.
I mean, clarify in terms of some, counting vertices of trees.
Yeah, if you like. I mean, you've got, can we clarify it in terms of counting vertices of trees? Yeah, so if you just have a single countable valence tree, right? So how do you go, so I've got, an n's worth of places I can go here, an n's worth of places I can go here, and n's worth of places I can go here, etc. So I start with my root vertex here, and then I do this. I go one up the first branch, and now I go one up the second branch, and then I attach a leaf to every node that I've got so far. Well, sorry, yeah. So at each stage, you just attach another leaf to every node that's appeared so far. Does that make sense? Okay. So then this happens in the second place, and then I need to attach something here. And now I do attach something to the 0 node, and then attach something to this 2 node, and something to this 1 node, and then something to this 3 node, etc. I mean, so there's a way to kind of interleave, it's how you mimic a process with infinitely, let me say it this way. So if you have a program with 2 threads, you can run it on a single Turing machine just by alternating, right? But in fact, if you have a process with infinitely many threads, you can mimic on a single Turing machine by doing something like what I'm talking about. Any given thread might not start for a while, but it will eventually start.
At each node you have the continuity.
Yeah. And I'll eventually list any particular vertex I'll eventually get to. And at any stage, I only have a finite valence tree, but its valence is growing all the time. There are lots of different ways to do this. It's probably easier to work it out for yourselves than to try and understand this picture I drew. This is clear to everybody at least what I'm claiming. Okay, good. All right, so this makes our job much easier when we want to try and decide, for example, A2. So it says that if A2 is satisfied, we'll eventually discover it by this brute force enumeration. So the main work is in certifying that A2 does not hold for a particular presentation. So the sort of BFE lemma implies that if G satisfies A2, we will eventually discover it. So to get an algorithm, we need to be able to certify with some finite amount of data that G, a goose whip, does not satisfy A. So the certificate that I described last time, was to do with this factor set. Let me just remind you what it was. So the certificate we use is one of the three possible things. So one, a factor set. Remember, one of the things we showed was that for any goose whip we can compute this factor set, which is a kind of way to understand the set of homomorphisms from your group to a free group, right? A way to kind of decompose it into homomorphisms that factor through certain limit groups. So it's a factor set A to I from G to Li with more than one element in it. So that was bad, or that was good. It told us we weren't looking at a surface group. Or a factor set with just a single element in it, so that L is not a surface group. And here, in order for this to make sense, we need to be able to tell which limit groups are surface groups. And that used either this work of Demani Groves or this work of Omegan, Karlopovich, and Yasenkov. Or 3, a factor set where L was a surface group. And an element of the kernel. So that was how we did A2, maybe a little differently organized than the way I rapidly said it at the end of last time. Okay, so the main thing I want to get across for the purposes of understanding A3 is this two-part model that if we can list at least one, presentations that are in our class we're trying to recognize, and we can get only presentations of groups in that class and at least one pro-isomorphism class in that class, then we have a way to certify that a given group is in the class, right? And then all we have to do to finish the algorithm is come up with a way to certify that it's not in the class. And these two are, separate. So this is something we got confused about many, many times while talking through this algorithm. So that's maybe why I'm overemphasizing it. So let's move on to A3. So we again divide into two parts. First, we need to show that the set of presentations of closed, orientable, aspherical, three-manifold groups is recursively enumerable, and there's nothing new here. But I will explain it though, I hope. And then second, be able to certify that a given group of solvable word problem is not such a presentation. Okay. So the hard work is here, but let me say how you do the first part. Which is that, so presentations I'll just say three manifolds for sure. So aspherical three manifolds recursively enumerable. Or the set of presentations is recursively enumerable. Okay, so the first point is an old theorem of Bing and Louise, which is that if you have a closed three manifold, in particular closed orientable three manifold, it's triangulable, and in essentially a unique way, but we won't use that. Just that it has a triangulation, so this is something that starts to fail when you go into higher dimensions. Okay. So if I list all possible three-dimensional triangulations, I will have a list that contains all of the groups, at least one presentation for all the groups that I'm interested in. It also contains a bunch of extra stuff I need to be able to throw away. But let me just point out that the set of finite three-dimensional triangulations is clearly recursively enumerable. So we would say closed, orientable, three manifolds is recursively enumerable, right? So I just think about, any particular triangulation has some number of tetrahedra in it. It's a finite list of ways I can glue that number of tetrahedra together, and I can list all those different ways of doing it, right? And now I can check, if I have such a thing, is that the link at every vertex is a sphere, which it better be if I'm going to get a manifold, and that I haven't glued things together in the wrong way so that I get an orientation reversing loop somewhere. So that's that. So now we need to be able to test asphericity. So
Is length really crucial here?
I don't know. I mean, if it's not, it's pretty easy. I don't know. Yeah. So it is crucial because I'm only interested. I'm trying to enumerate fundamental groups of closed aspherical orientable three manifolds. Maybe you're asking a more general question, which is orientable crucial? I don't think so. No. Yeah. In general, when we talk about M3, we want to split. It makes things more convenient if things are orientable. Because things are not orientable, we may need to split along RP2s and not just S2s. I don't know. And that's different.
I'm just thinking about
Yeah.
it's no lemma.
Yeah, and the lemma? Oh,
I
yeah.
don't see any.
No.
I mean, the lemma that you just see, the set of finite triangulations of closed orientable.
No. They're both the set of orientable, and that's actually important. Yeah, the set of orientable ones is recursively enumerable, so is the set of non-orientable ones, correct? And so that's going to mean that the set of presentations of non-orientable three manifolds is recursively enumerable. So in fact, if we were given one of those things, which is like almost the kind of thing we're looking for, but not quite, we'll eventually discover that. And that's one of the subtle points I was going to totally ignore, but I'm glad you brought it up because that's, yeah. So that we can recognize if something is a non-orientable three manifold as well. So it's a three-dimensional complex. So we need to look at pi 2, we need to look at pi 3. So to be able to test, for this given presentation, that pi 2 of m, or this given triangulation, pi 2 of m is 0, and pi 3 of m is equal to 0. And so then here's where I start using some real three manifold theorems on so first of all, there's something called the sphere theorem. So the sphere of Papakiriakopoulos, which says that if pi 2 of a three manifold, which is, say, orientable, is not 0, there is an essential sphere, an essential two-sphere embedded. In M. And now there's a lot of right. So I think Waldhausen and Hawkins started this. If you have an essential two-sphere, you can find one that's in a very nice, what's called normal position with respect to the triangulation. And so it's a finite algorithmic procedure to list all the possible essential two-spheres. So, well, that's not obvious even from what I said, but it's true. So I think I want to attribute this to Waldhausen, or maybe to Hawkins. So there's an essential two-sphere. It is one of finitely many. So this is, again, we're working with a fixed triangulation of a three manifold, and we're trying to decide do we worry about the presentation of this, or is it a non-aspherical three-manifold that we should throw away and ignore our list? Yeah. One of a finite, computable, constructible collection of two spheres. And then there's work of Rubinstein and Thomson, plus the Poincare conjecture, says that we can tell if a given such sphere represents something non-trivial in pi 2. Okay. So we've got a triangulation. Haken, and I should probably write Waldhausen here as well, just to be safe. There's a finite procedure to come up with a list of candidate two spheres, and then if none of those is essential, then pi 2 is trivial, and at least we don't have any pi 2. So if pi 2 is 0, we want to check. So then, again, so now I'm going to use something from the geometrization conjecture. Which, this is the finite fundamental group part, which I'm not going to go into detail about, but it implies that pi 2 is equal to 0 and pi 3 is not equal to 0, then the geometrization conjecture implies that there is an at most 60-fold cover, which is something called a lens space. So a lens space is what you get when you take a pair of solid tori and you glue them together along the boundary. A pair of solid tori glued together along the boundary. It's got cyclic fundamental group. And then there's an algorithm of Rubinstein, which so deciding whether a given three-manifold is a lens space is decidable. So what do? We've got our manifold M. Suppose we've checked that pi 2 vanishes. Now we can build all the possible 60-fold covers and test to see if any of them is a lens space. If it is a lens space, pi 3 is non-trivial, and we throw it away. But if none of those up to 60-fold covers are lens spaces, then in fact pi 3 has to vanish. So pi 3 non-vanishing really just, if pi 2 vanishes but pi 3 doesn't vanish, that just means the universal cover is S3. That's one of the things that geometrization conjecture says. So that's what we're testing. Okay, so we can verify, we can test whether pi 3 equals 0 by applying Rubinstein's algorithm to all less than or equal to 60-degree covers. Okay.
Just, I kind of, maybe this is a technical issue, but
Sure.
if you're just enumerating all these three manifolds somehow,
Yeah.
triangulations, can't you just sort of look at each one in turn and see whether it is very obviously, hyperbolic or hyperbolic with the big JSJ decomposition, right? I mean, it might just happen that the triangulation happens to be one that the first thing you try when you try to geometrize it happens to be extremely close to the hyperbolic structure. And so you very quickly verify that you've enumerated the hyperbolic manifold. If you're enumerating all triangulations of all three manifolds anyway,
Yeah.
this is sort of, if you fail to easily satisfy this, throw it away, we don't care. We know that a good one's going to turn up eventually.
Yeah, but I mean, you're trying to enumerate all the spherical three manifolds.
But you know exactly what they are.
Huh?
You know exactly what they are.
Yes.
So you wait until you just see one which obviously is one of them. You don't have to test that every single one of them.
Okay, yeah, I believe that, yeah, okay, sure. That probably works, yeah.
I mean,
Yeah, absolutely, yeah.
I'm just wondering why you're going through all this.
Well, I don't know, you're right, maybe there are easier ways to do it, because we know what three manifolds look like.
Yeah. I know
Right.
what a spherical three manifolds look like, and you might happen to have a triangulation which very obviously is one.
Yeah, okay. I think you can do it that
And
way.
eventually,
Yeah.
every.
I think you can do it that way. I think that's fine. Yeah, but I mean, you also need to build the ones with non-trivial JSJ, and you need to build the
Which are obviously just there in the two six.
Yeah, I'm trying to be as simple-minded as possible about this. I mean,
Okay.
maybe this isn't as simple-minded as possible.
I mean, using like the Poincaré conjecture, Einstein, Thompson, whatever it was.
You have to. I think you have to. Well, no, maybe you don't. You have to use the Poincaré conjecture, but... not to get presentations, right? Okay. Yeah. I think you're right. Anyway, at this point, I've established that the set that you can enumerate using the BFE lemma and the fact that triangulation gives you some presentation plus the BFE lemma. This tells you what I was trying to show, which is that the first part. So there's a sort of corollary. The set of aspherical. So presentations satisfying A3 is recursively movable. Yeah, that's right. I should say, I mean, I should have said this several times earlier, but this is all, I mean, we don't have a preprint yet, so this is in some sense work in progress, right? So I'm happy to hear about more efficient ways to do things, because, yeah. Okay, so now the key thing that we need to be able to do is to certify that a given presentation is not the fundamental group of any closed aspherical orientable three manifold. So it does not satisfy A3. So now here, I really need to use, so the certificate is going to be a combination of certificates. So here's some examples of aspherical three manifolds. So we say that, and I'll do it in terms of properties like A3, and the point is that, one or the first or the second or the third or the fourth is the same as A3. So we say that G satisfies H if G is the fundamental group of a closed orientable hyperbolic three manifold. So G satisfies, we'll just write SFS less than or equal to 0. And now here I'm going to give you some undefined terms that I'll define probably later. So pi1 of a Seifert firing space with Euler characteristic of the base orbifold. Don't worry if you don't know what that means yet. Non-positive. So these Seifert firing spaces are kind of important three manifolds which are decomposed in a natural way into circles. And the space of circles is itself a two-dimensional orbifold, and that's what this base orbifold is. If the Euler characteristic is positive, then you can't be aspherical, is the point. So Euler characteristic non-positive is aspherical. And then we'll say G satisfies Sol. This is a separate, we need to put this in, for reasons you'll see, I need to handle this one separately. If G is equal to pi1 of, well, a solved manifold. Three-dimensional solved manifold. So I need to tell you what that is. Maybe. I might skip that. Basically, if you don't know, these are certain kinds of, they're always finitely covered by a torus bundle over a circle with a certain kind of monodromy, where the monodromy is an Nosov, so it has non-real eigenvalues, and isn't finite order. Sorry, non-real, it has two distinct real eigenvalues. Sorry. Yeah. If they're, in a torus bundle with complex eigenvalues, we're going to end up in this situation. And then G satisfies acylindrical JSJ if something called the torus decomposition, so G is equal to pi1 of a three manifold with non-trivial or acylindrical torus decomposition. Okay, now, so the geometrization theorem, so I haven't defined a lot of stuff that I need to define, but let me just say another way to state the geometrization conjecture, which is now a theorem. And we'll say it implies, because this is really just the infinite fundamental group part, is that A3 is equivalent to H or SFS less or equal to 0 for Sol or acylindrical JSJ. So every aspherical three manifold falls into one of these four boxes. So we need to, so a certificate that we don't satisfy A3 is going to be composed of four separate certificates. A certificate that it's not hyperbolic, a certificate that it's not Seifert fibered with non-positive or the characteristic base orbifold, a certificate that it's not Sol, and a certificate that it's not one of these kind of manifolds with non-trivial JSJ. Not H, not okay. And I'll say something, I guess I've got 50, well, about 10 minutes left today. So hopefully I'll say something about this one, and I'll start to say something about this one. So this is by far the hardest certificate to obtain in general, to be sure that you've got. So let me just briefly say something about the first one, about certifying not H. So this is based on some ideas Casson, CF, a paper of mine in GNT number 6. Anyway, the first paper in that. So, this was the first thing my advisor asked me to do in grad school, and then I didn't prove anything about 3 manifolds, and it's kind of fun to come back. I like 3 manifolds. Okay, so anyway, so the idea is that what does it mean to be hyperbolic? So I guess hyperbolic manifolds have come up several times, but so it means that if you're hyperbolic, that means that you have this nice Riemannian metric of constant curvature -1, right? Which means that if you look at the sort of what this gives you is a representation from the fundamental group to isometries of hyperbolic space, right? Which is a nice linear group. Okay, so we can construct the representation variety into that group, and that's what we're going to do first. So, given, let me just say the sort of fact we're going to use is that G satisfies H if and only if there is some a discrete faithful representation rho from G to isom plus of H3, which is isomorphic to ESL to C, with which is rigid, and I'll say what that means in a second, and has no parabolics or elliptics in its image. So if you study the isometries of hyperbolic plane, for example, so an elliptic is something like a rotation, something with a fixed point, so we shouldn't see any of those. And then a parabolic, if you think of the upper half space model, is just move everything over to the, I guess that's your right. So, so that's a parabolic. And the point about parabolics is they have, translation length 0, in the sense they're points that are moved less and less. So that's not going to show up in a co-compact group. Now, in fact, I can lift this thing to SL2C. So this is a two-fold cover, and that's convenient to do. This is also true. And that's convenient because this idea of being elliptic or parabolic, then you can understand in terms of the trace of a matrix. I mean, you can understand it in terms of sort of trace squared here, take a representative square as trace, but it's sort of convenient to work over SL2C. Okay. So, and what does the rigid part mean? Well, I'll tell you this by telling you what's the representation variety and the character variety. So, this is R. It's not really a variety. It's an algebraic set. We'll just call it R of G, which is from G to SL to C. Okay, so that's some algebraic set. And why is it an algebraic set? Well, I can think of the generators. I have these n generators here. And so to specify a representation, I need to tell you n 2x2 matrices. Right? So that's 4n variables. So I'm living in this affine space, which is 4n dimensional. Each of these determinant conditions, that's polynomial in the entries of the matrices. And now the relations, I have a finitely presented group. Each of the relations gives me 4 more polynomials. It says that this product of matrices is supposed to be the identity. So this is an algebraic set. So maybe more surprising is that the character variety I'm going to take this set, we'll write x of g, and I look at r of g, and I take this sort of quotient by the conjugation action of SL2C on the image, right? So if I take a representation, and then I look at the same representation conjugated by some matrix, I don't want to regard those as different. I want to regard them as the same. So I quotient out by that action, I get something called the character variety. So, and we'll say that a representation, and again, it's not really a variety, it's just some algebraic set, is rigid if is a zero-dimensional component if its equivalence class is a zero-dimensional component of this character variety. Right. So I have some algebraic set here divided up into a bunch of different varieties. Some of them, they have various different dimensions. The representations I care about are rigid, and so they're going to show up as zero-dimensional components of this variety. So now, so using tools from computational algebraic geometry, means that we can list the rigid representations. So rho 1, rho n, a collection of rigid representations so that any rigid representation is conjugate to one of these. And so that rho I doesn't just map from G into SL2C, but it actually winds up in this nice computable subgroup. Not Q, but Q bar, right? I've got algebraic entries in my matrices. So I can do any kind of computation that I want with these guys. Okay, and now I'm going to go just 1 minute over. I want to say what you do with these things. So to certify not H, we just need for each rho I to show one, so one of the following, rho I is not faithful, rho I has an elliptic or parabolic in the image. Are there 4 things or only 2 things? I think I just want to say, oh right, or it has is reducible. This actually doesn't come up, but let me ignore that. We'll just say is indiscrete. By that I mean has an indiscrete image. And how do you verify that? I'm glad you asked. So that so what you want to do is you look for a violation of Margulis lemma. So you want to look for 2 elements that don't commute. You can test that they don't commute by using the word problem. And that so that if you look at the matrices and look at what they do to a particular point in H3, they both move it not very far. Okay. So that tells you you're going to be either indiscrete or unfaithful if that happens. And then, yeah, so that's, the others, it's fairly clear what you do, I think, to certify that one of those is happening. So now this is this finite procedure. If it's not, if the group doesn't satisfy H, all these representations will be bad in some way, and we can discover how they're bad in some finite amount of time. And so that tells you how you certify not H. And I'll stop there for today.